My name is Luca Ferry. I'm a second year PhD student working at LSE in France. And today I'm going to talk about work we did with my supervisor, David Faranda, about the derechos. So derechos are a category of convective storm. They have been defined by a meteorologist, an American meteorologist in the 19th century, as a type of widespread convective windstorm, and they are associated with extratropical mesoscale convective system. So a mesoscale convective system is a complex of a cluster of thunderstorms that span more than 100 kilometers wide. So in the right picture, you have a radar display, weather radar display at 6 a.m. on the 18 August 2022, where you can see a patch of a red patch that correspond to high precipitation rates. So this is a snapshot of a very severe convective storm, a mesoscale convective system. So you can see it has a bow linear shape that has about the size of Corsica, the island, the French island in the Mediterranean. And it is about to hit this island. So this is an example of such a storm, but we need more features to define a derecho. Derecho must produce a lot of severe wind gusts along a very long path. So on the left picture, you can see a depiction of this event where each yellow square represents a strong wind gust report. And you can see that the storm initiated, so in the bottom left around the Balearic Islands, and it propagated all the way to Czech Republic within 16 hours. So the red dashed line represents the position of the mesoscale convective system at different times during this day. So the trajectory span more than about 1,500 kilometers, and it produced the storm produced very strong wind gusts reaching about more than 200 kilometers per hour in Corsica, reaching the record of the corresponding weather station. So those storms are very severe. So again, here are some figures about this event. So on the right picture, you have the representation of the lightning strikes colored by their timestamp from red to white. So you can see we have a lot of lightnings and coherent progression, chronological progression. So yeah, this storm lasted 16 hours. It propagated over a very long distance, produced very strong wind gusts. It caused several casualties and injuries, and also widespread damage. So on the bottom left, you have some boats that were damaged by the storm in Corsica, and on the bottom right, you have a beautiful picture of the line of thunderstorms before it made landfall in Corsica. So this is a very typical shape, very typical feature of this mesoscale convective systems. So derechos are quite well-documented phenomena in the USA, where there have been several studies since the 1980s, more specifically. But in Europe, there is little research on the subject. There are a few single case studies and two more comprehensive studies with climatology for Germany and Poland. However, we are still lacking analysis in other countries and at the European scale. So we wanted to to study these storms in France and to be able to say how frequent they were. And also in the second part, we were interested in the effect of climate change, the potential effect of climate change on their intensity and frequency. And actually, it's a quite difficult subject to study the link between climate change and convective storms. So there is up to now little knowledge about how climate change affect those storms. Specifically, there are uncertain trends in, for example, convective parameters, such as ones that characterize the instability, the convective instability. But also when we study trends in convective hazard, for example, hail or wind, or more directly, the frequency of convective storms, we don't have very strong conclusions, and when we have some, they are sometimes conflicting and depend on the region where we are interested in. However, what we can say at least is that there is a consensus that there is increased rainfall rates and volume associated with mesoscale convective systems. And here I show you a table from a review paper on MCS. And so, yeah, you can see that for rainfall, we have a high confidence in increase for these storms. But it's more difficult to give answers about frequency, for example, of those type of storms, or even of environment that are supportive for this type of storms. And we have also conflicting results for convective inhibition, for example. It is quite difficult, actually, to study the link between climate change and convective storms, for instance, because it is not as easy to define, to give a common definition of convective storms. For example, when we try to detect them in observational studies, the definition is not always obvious, and different studies use different definitions. Also, more importantly, there is a lack of good quality and long-term observational data set. Specifically for satellite and radar observations, we have maybe 40 years of data maximum, so it's difficult to derive trends from this data. And sometimes the coverage is not global also. Convective storms are also influenced by natural variability. So it can be modes like ENSO, but also teleconnection patterns. And when we want to use climate models, it's also difficult because convection is not resolved in the climate models that are used to make projections. Although we can use regional climate models or convection permitting models that are better in this task, but that have a lot of computational burden. So, so in the first part, I will describe how we try to detect past events in France. So to do so, we used two types of data sets. So the first one is wind gust speed measurements from weather stations, so mainly from Météo France, but also from other data sets. And also we used severe wind gust reports that do not necessarily come from wind speed measurements from weather stations, but also from damage reports. And those are reported in a database called ESWD, maintained by the European Severe Storms Laboratory. And so on the second hand, we use geostationary satellite data with two variables. So infrared brightness temperature, which is a proxy of the cloud height. Indeed, convective storms are characterized by high clouds that span the whole column of the troposphere. So the top of these clouds that we can see from a satellite, they are cold because of the ambient temperature, and we can identify them from this kind of maps. Here we see a blue patch that corresponds to MCS with cold temperature. And along brightness temperature, we also use precipitation rate derived from satellite data. So convective storms are also characterized by strong precipitation, so high precipitation rates. So we use the following procedure. We first select days with more than 5 severe wind gust reports, knowing that severe wind gust is usually defined as being above 25 meters per second or 90 kilometers per hour. And then we check that we have a concentrated area of gust reports that meets several criteria. So we need that's the area over which we have strong wind gusts span more than 400 kilometers in its longest dimension. And also we require that successive wind gust reports must be close enough in space and time. So these criteria are inspired from the literature. There is not a consensus on how to choose them, so they can differ from a paper to another. But mainly, this 400 kilometer threshold is very often used to define a derecho. Then we check that we have an associated mesoscale convective system. So for this, we use detection and tracking algorithm that was developed by Feng et al. So for this, we use satellite data. And finally, we check that we have a coherent chronological progression and that the gust reports match in time and space with the MCS. So finally, we got these results. So we studied a 23 years period between 2000 and 2022, mainly because of the limited time coverage of satellite data. And specifically, we focused on the warm season, so between May and September. We found 38 events in total. So the average is 1.7 per year, but there are significant variations from year to year. So we can have years without any event, and some years we can have more than we can have 5 events, for example. So on the left picture, you see the tracks of these events. So there are different colors that correspond to different intensities, but I will explain it a bit later. But maybe the most striking feature is that most of the trajectories have a similar direction from the southwest to the northeast. And indeed, when we look at the associated circulation patterns, we see that we have very often a trough or a cutoff low situated on the western part of Europe. So these storms tend to develop ahead of these trough or cutoff lows, which is also a known feature for the storms. And we can also have a look on the right picture at local frequencies. So we divided France into squares of 200 by 200 kilometers to compare with climatological studies led in Germany or the United States. So we can see that almost all the territory is affected by the storms, but we have higher frequencies in the northeast, which also match with a frequencies observed in Germany, where we have higher frequencies in the south of Germany. And actually, many, as you can see on the left, many of those storms are they affect the northeast of France and the south of Germany, southwest. So yeah, then we classify the events into 3 categories of intensity. So for low intensity, we do not have any additional requirements. Although for moderate intensity, we require that at least 3 reports have measured wind gust speeds over 33 meters per second. And for high intensity, we also require 3 reports over 38 meters per second. So on the bottom, you have histograms of intensity, bottom left. So you can see that most events have low intensity. So very intense events, such as the one from 2022 that affected the Mediterranean, are quite rare. We have only four instances for such strong events. So if I come back to the map, you see that the high intensity events are colored in purple, the moderate ones are colored in blue, and the low intensity ones are colored in gray. And yeah, the 2022 event is also very particular, as you can see, because it occurred in the Mediterranean, whereas most of the other events occur mainly over the continent. So that is also a difference, which can partially be due to the lack of measurements and weather station over the sea, but it is also an observed feature in the United States, for example, that most of these events affect the land and only marginally the sea or the ocean. So we focused on the warm season, and as you can see on the bottom right picture, the seasonal frequency peaks in July, August. So this is similar to what is observed in Germany, but maybe we have a bit more events in the late season, which can be due to the presence of the Mediterranean Sea, which provides moisture and heat late in the season. So this is similar to what is observed in the fall season. So now I move on to a second part where we were interested in studying synoptic and environmental changes associated with the storms. So we adopt a methodology where we condition on atmospheric circulation that are conducive to these severe convective storms. So we search for past analogs of atmospheric circulation associated to each event. And we focus specifically on the map of geopotential height at 500 hectopascal, from which we just subtracted the mean value to keep only the circulation pattern without taking into account potential thermodynamic effect. Then we split the historical period into 2 periods. So there is a more distant period in the past between 1950 and 1980 that serves as a counterfactual period where global warming was lower than today, and more recent period between 1992 and 2022 that serves as a factual period. And we take the 37 best analogs in each period. Then we compare composites of several variables, all from era 5, associated to these analogs in the 2 periods. So geopotential height, 2-meter temperature, daily cumulative precipitation, wind speed, and more importantly, 2 proxies that are very important to characterize synoptic situation in terms of probabilities of having convective storms, which are CAPE, convective available potential energy, that characterizes convective instability, and deep layer shear, which is the vertical wind shear. It's the vector difference between the horizontal wind at 500 hectopascal and 10 meters above ground. And this is important because it helps to get an organization of convection at the mesoscale, so which helps developing clusters of thunderstorms, such as mesoscale convective systems. So here you can see these variables, these maps for the 18 August 2022 events. So you have that 500. So we have a cutoff low that is located over the northwestern Mediterranean. So we had high temperatures over the Mediterranean Sea. At the time, there was a marine heat wave, so the sea surface temperature was also very high. And then you can see the daily cumulative precipitation. So we have a lot of precipitation over Italy, wind speed, nothing particular, but more importantly, we had very high values of convective available potential energy over the Mediterranean, and also significant wind shear associated with the presence of this cutoff flow. So the conditions were very favorable for the development of a severe convective episode. Now I show the results of this analysis for the 18 August 2022 event. So on the first line, you can see the patterns of geopotential height. So the first column corresponds to the past period, and the second column to the present period. And the final column is the difference between the two composites. So you can see we have good analogs because we don't have any significant change in the circulation pattern. 2-meter temperature, we see that we have higher temperatures over most of the continent and over the Mediterranean also. Precipitation is a bit more difficult to interpret, but we observe a decrease of precipitation in northern Italy. So wind speed, there is nothing special to notice. And now when we look at Cape, we see a strong increase of Cape, marked increase over the Mediterranean in the area where the storm developed. And for wind shear, so DLS, we don't see any change in this region. So we replicate the same analysis for the 38 events. So here is a table summarizing everything, but the important conclusions are that, of course, we observe an increase of 2-meter temperature in most of the cases. But the most important thing is that we have an increase of CAPE, of convective available potential in energy in most of the cases. We have more difficult to interpret results for precipitation. In almost half cases, we have increase of precipitation, but also in 20% we have a decrease, so it's not easy to interpret. What is also striking is that we observe changes in circulation patterns in most of the cases. So in the map I showed you, we had no change in the circulation as encoded in the geopotential height. However, for several events, we observe shifts in the circulation pattern. Maybe this is due to the large window, the large geographical region we focused on, because it encompasses most whole Europe. But that makes any conclusions on on the role of climate change a bit difficult to make. And it is all the more true because we cannot exclude influence of natural variability, mainly from ENSO and AMO, by comparing the distribution of the syntheses in the two periods. So to conclude, we have identified 38 warm season derechos in France in a 23 years period using wind gust reports and satellite imagery. The average frequency, the national scale is about 1.7 per year. And if we compare local frequencies, so by standardized grid box, we have similar frequencies and features as in Germany, but in the USA you can have more than a double frequency in some places in the Midwest, for example. So also what was important is that most of the events are much less intense than the 2022 events, which was very particular, also by its location and trajectory over the Mediterranean. And then we observed an increase of instability conditioned on this circulation pattern in the recent period, which is in agreement with several other studies that point in the same direction. And this might translate into more intense storms in the future. But it is a bit difficult to make a strong statement, as these are indirect variables, proxies, and not direct estimation of intensity. So of course, further work is needed. For example, to examine radar structures and other environmental conditions that are relevant. So for example, convective inhibition that prevent storm to initiate, although we can have significant instability. And the role of climate change versus internal viability also needs to be clarified. So thank you for your attention, and I will be happy to take any questions if you have some.
Thank you very much, Lucas. Is someone willing to ask a question? Let us know. You can raise your hand or you can just speak. No questions? Okay. Oh yeah, there are. So let's start with Pascal.
Thank you, Luca. It's just a naive question. So, do you know if there are examples in the past, in history, of such events that struck the Mediterranean or France or wherever? Because this came out in a way out of the blue, but do you know if there are examples of such events?
In the Mediterranean specifically?
Yes.
So our study focuses mainly on France. So we have another example that partly affected the Mediterranean. So I don't know, maybe you cannot see my mouse, but if you look at the left figure, you have a blue trajectory that passes over the Gulf of Lion a little bit. It initiated in Spain, in northeastern Spain. So there is a part of its path over the Mediterranean, and it initiated on the Spanish coast. So maybe this is the most similar example we have. But
Because So
to be
when
more.
when
Yeah,
was that?
it was in 2003, so during the heat wave, I guess, in August. But to give a more precise answer, we would need to focus on to look at events in other countries also. The thing is that the data sets, for example, the weather stations, there is no common data set at the European scale, to my knowledge. So it's a bit tricky to do those kind of studies in more than one country at once. Or it requires a lot of time to get access to the data because it's not always publicly available. But yeah, it would be necessary to study cases in, for example, Spain, Italy, Greece. Yeah.
Okay, thank you.
I guess, Frank, go ahead.
Hi, Luca.
Hi.
Nice to meet you and very good presentation. I have some question on this slide. Do you hear me? Is it okay?
Yeah, sure. Yeah.
Okay, thank you so much. When you compare the APE between past and actual, you show an increase in south of France. But
Increase of Cape, you mean?
yeah,
Okay.
yes.
Okay. Here, maybe.
Yes. Here, yes.
Yeah.
We can see an increase in Corsica or Sardinia.
Yeah.
But when I watch the slide 11, you show
This
an
one.
increasing in frequency in northeastern in France. So how did you explain this different information? And my other question is how did you explain the start of derecho in the France, in the continental territory of France?
So for your first question, I'm not completely sure I understood, but on the right picture here, I show the yearly mean derecho frequency. So it's not a trend. I'm not saying here that there is an increase in frequency in the northeast. It's just that we observed higher frequency historically here. I think as we have too few events, those are still rare events. We have low sample size and it's difficult to derive any significant trend from this data. And for your second question about the initiation of the storms.
Yes.
This is a bit difficult, I think, because at least I'm not an expert in this field, like a meteorologist. The question of the initiation of storms is a bit complex because we can have a favorable situation where we have instability, for instance, and wind shear also. Wind shear is more important, as I said, to have an organization of storms at the mesoscale, which enable a longer-lived storm that kind of sustain itself, that can survive a long time, and this way create more wind gusts, for example. So those proxies we can look at from the large scale in some sense. They give you some probability maybe of having a storm. But there are other factors at play. For example, we have convective inhibition. So in order to have a release of the instability, the latent energy, we need that parcel of air that are close to the ground pass through this kind of barrier of energy to then release all the latent instability and produce storms. And that can be that can happen if you have a front, for example, that will lift the parcel of air very quickly, or with the orography. But those are very local scale features, local scale mechanisms that are very difficult to predict. So I don't have a definite answer about this. I think we have more to think maybe in terms of probability given synoptic and environmental situation.
Thank you.
Actually, for the 2022 event, the one that affected Corsica, the AROM, the model of Météo France, did not forecast such an intense event. So that shows that even the best models really struggle to forecast this type of storms because they are very sensitive on, for example, surface temperature, humidity, and shifts in fronts, for example. So Météo France issued, I think, a yellow alert, whereas so they released the red alert too late, just when the storm made landfall in Corsica, and so it was too late to prevent casualties and damage. So it's also tricky to forecast the storms.
Okay. I have another question. Do you observe a modification of trajectory during this past 30 years or 20 years?
Again, I would say it's difficult to derive significant trends because of the few events we have. We have only 38. So yeah, I would say it's very difficult to point any shift. Yeah, maybe indirectly we can look at trends in circulation patterns that are associated to those events, because when we look at the circulation patterns, for example, for these events, the storm, we see that it really developed along the isolines of geopotential height here. So the circulation pattern is really it really conditions the event. So if we look at, for example, if this circulation pattern is going to appear more often, that is easier to look at, then we can say maybe this trajectory will be more likely, this kind of storms will be more likely. But we actually look at trends in those circulation patterns, but so here in the table, but we have only a few of them, 5, where we have a significant increasing trend. So, and usually it's not very high, the trend. So I would say it's difficult to conclude anything from this.
Okay, thank you. Thank you very much.
If I
Thank
can
you.
add on top of what Luca said, I think that this problem of forecasting these events that are very intense and they are driven both by high altitude winds and sea surface temperature is now, I think, well known in the weather community. And the very last example is the hurricanes Beryl that is hitting now the Caribbean. Again, like it's a freak event with a lot of energy into play, and where very little changes in the upper level circulation can change the forecast by a lot. So these phenomena are by definition very sensitive to the initial conditions, so it's difficult to forecast their genesis. It's easier once they are at their maximum stage to say where they will go. That's, for example, the case for beryl that now it's been well predicted since like yesterday and 2 days ago. Same, I think, Luca, for the derecho. Once the derecho was there, it was tracked by the analysis, then the impacts in Toscana and in the northern Italy were better anticipated, although the damages were still very important. So the genesis of this phenomenon is really interesting, and it's a point that I mean, even the best weather models, the convection permitting weather model struggles. So there is a lot of research in this field.
Thank you. Are there more questions? Melinda has one. Go ahead.
Yes, hi.
Hi.
Thank you very much. Very nice presentation.
Thanks.
What I noticed based on the trajectories is that for the less severe events, you have basically it seems to be that you have two dominating trajectories, one closer to the Alps region and the other one closer to the North Atlantic.
Yeah.
And then for the very extreme events, you have like quite very different trajectories. So I was wondering if you can relate these to different circulation anomalies. Like, what have you observed? How do this like indeed like how similar are the circulation anomalies, and do you see the corresponding changes in the circulation anomalies to these corresponding to these trajectories?
Thank you for your question. Well, I agree that we can maybe divide into 2 or 3 categories of trajectories. Yeah, indeed, we have several trajectories initiating north of the Alps, for example, and significant number in the north of France, but we also have some of them in the southwest. So I didn't specifically look into the potential differences into the circulation associated to the very intense events. So yeah, I don't have a real conclusion on this. Yeah. But I think it would be interesting to maybe do some cluster analysis of the circulation patterns, to investigate a bit more the ones that are similar, and if we see different trends associated to the different patterns. But for example, sorry. So the very intense event that occurred up to Denmark. Well, I would say it's not. It's probably similar the circulation pattern to the other ones, the other surrounding ones. So I'm not sure there is a difference in nature of the pattern. Maybe there was a bit more instability or more wind shear. But I didn't look specifically into that. But it would be interesting to do here.
Yeah, thank you.
Thanks.
Thank you. Any more questions? I guess not. If so, then I would like to thank Luca again for presenting and everyone participating.
Thank you very much.
And
thank you, Luca.
Thank you.
And
Thanks.
we see each other soon.
Yeah. Bye-bye.
Thanks. Bye-bye.
Bye.
Ciao.
Thank you. Bye bye.